Across Newcastle and the Hunter, 2NURFM 103.7. It's always good when you can chat with some interesting people doing some very interesting things. And our next guest is doing just that. He's from the University of Newcastle, doing a PhD at the moment, and a whole host of stuff in and around chemical engineering. And I'll probably burst the bubble. We're going straight to the end that those that may benefit out of this will save a couple of bucks. Some big bucks. His name is Josh Starrett. And Josh, firstly, thank you so much for your time. We'll get into the whole mineral processing thing that you're studying doing at the moment. But first up, chemical engineering, how, why, and what was the spark that got you into that?
Yeah, no, good.
And we have a bona fide smart person, so welcome.
No, happy to serve. Chemical engineering is sort of one of those topics or subjects, I guess, that people don't know a lot about. Like, it sort of sounds like, I guess it's a little bit sciencey. Like, I get the question all the time, do you engineer chemicals? Like, what do you do? But chemical engineering is sort of everything. I like to think of it a little bit like it's just someone that has some science know-how and you can sort of apply it to a lot of different industries.
All right, you're just missing the white lab coat pocket protector, but other than that. So we fast forward a little bit, and because it's always good to, like I said, people can be doing these really interesting things. And you fast forward to year one, and you're working with the Australian Research Council and looking at doing something with mineral processing. So how is that done now, and what are the things you're looking at to sort of make some changes there and do a whole lot of work in that area?
Yeah, so a part of the ARC Centre of Excellence in Minerals Processing, which is a group here at the University of Newcastle, and something that our group is sort of looking a lot at is making minerals processing more efficient. So reducing energy use, reducing water use, reducing wastage, because these sort of like what's coming out now, which is critical minerals. These things are really important for sort of, I guess, the future economy in terms of stuff for solar panels, stuff for electric cars, like these things that we're really going to need for that sort of carbon neutral future going forward. And so if we're going to need to really ramp up how much of this stuff we're going to need, then it's really important that we make it more efficient so that we can sort of reach those carbon neutral targets.
Well, the trick with a lot of these minerals is they're sort of rare earth, aren't they? There's not a ton of them around. So, I mean, you have to make hay while the sun shines, and you have to sort of make use of what is there. So with that in mind, anything that can sort of stretch that bit of chewing gum a bit further is probably going to garnish a lot of attention and thus save a couple of bucks on the way. So where exactly is the research heading at the moment with you?
Yeah, so what I'm looking at specifically is separating particles based on size. So in minerals processing, one of the major things that's important is this size separation step. So when you get these critical minerals, these rare earths out of the ground, something like a copper, for example, you might get this big, large rock out of the ground and there's a little bit of copper in it. So what they need to do on these minerals processing plants is they need to crush down these rocks so they can get the copper out of it. And so they chuck these just basically boulders into the crusher. They become really small, and you need a device that's able to get the particles that are small enough, move them on to the next stage, and pass those really big particles back into the crusher. But unfortunately, at the moment, the technology they've got doing this sort of job, the size classification devices, they're pretty inefficient. So they're sending a lot of stuff back.
It kind of sounds like it's still almost gold rush type of, isn't it really?
It's still, like, there's a lot to do. I mean, we need... I think I was just looking at a paper a little bit earlier where silicon's something that's in your phones, in your laptops, but also in those solar panels as well. Sort of the main sort of ingredient, I guess, in solar panels. There was a report by CSIRO that essentially said, about now we're using about 1 million kilograms or billion kilograms of silicon per year. And in sort of 30 years, that's going to need to be 30 times higher. So it's definitely something that's really ramping up at the moment.
And as well, particularly with like the waste as well, like I said, you chuck the big boulder in, and because you're looking for very fine particles, I can imagine that also some may just go out with the boulder as well. So, I mean, you want to make sure that whatever is in that piece of larger rock that you have, you want to make sure you capture every little bit.
Yeah, exactly right. It's really a case where, because these processes are so inefficient, they keep throwing these rocks back in again and again and again, getting crushed finer and finer and finer. It actually gets to the point that these rocks are getting too small to be able to actually collect. So because these size classification devices aren't doing a good enough job, we're just not only wasting energy in crushing these rocks up, which, as you can imagine, it's a pretty energy intensive process. I think it's like 2 to 3% of the global energy usage just on crushing rocks. Like, it's a big deal.
That's when you think of it. I mean, like 2% doesn't sound a lot, but 2% to actually not actually be getting to the end result is a lot.
Yeah, I mean, it's more energy than literally all of Australia is using. Like, it's a significant amount of energy that's being used around the world to crush these rocks.
When you look at those numbers like that, how long will the research take you? And fingers crossed, you might actually get to kick some goals on it.
Yeah, so I'm sort of approaching the 2-year mark of my PhD, and we've actually done a lot of really good work so far. So I'm sort of, I guess, exploring using this new technology, the reflux classifier, which has been developed here at the University of Newcastle, and sort of its ability to classify based on size. And we put out a paper a bit earlier this year, and we've done a lot of work, and it's actually been really, really, it's turned out to be pretty good. Like, it's doing a really efficient job at separating these particles. We're not throwing those particles back into the crusher, but we're also being able to do it at really high sort of rates, I guess, higher processing rates than even some current technologies can do. So we're sort of already shown, we're already proving that we can do it at high rates with high accuracy. And so it's actually looking really good so far, and I'm really looking forward to sort of the back half of this PhD.
Oh, it sounds like it's starting to come together, mate. As always, thanks for your time. Josh Starrett, University of Newcastle PhD student, chemical engineer and rock crusher. Good luck with it and see how it goes, mate. Pleasure.
Cheers, Mark.
2NURFM 103.7.
A broadcast service of the University of Newcastle.